In the next few chapters, we'll be discussing forces and studying forces and the application of Newton's laws of motion to problems where you have multiple forces acting on an object. But before we get to studying forces, let's just a quick recap of what we have done so far. So far, what we have done is we've introduced physical quantities like displacement, velocity, and acceleration that are important in our description of motion. And we also looked at certain types of motion, constant acceleration motion, and wrote down equations that relate these various quantities. The question that we are asking now is what causes motion? So just to make this very clear, so far if I show you an object, if you are observing an object that is moving, you know the kind of quantities that you need to define in order to describe its motion. But the question that we're asking is, well, how do you get an object to start moving? Okay, or if an object is moving, what do you need to do to change its motion, to stop it, or make it move faster or slower, whatever it may be. Okay, so the question is what causes motion. Another way to ask the same question, and in fact this was the way in the past it was thought of, as what is the natural state of motion of an object, meaning what if you have an object, what is the object most likely to do? If you left to itself, what would this object do? And now this is an old question. There were many people addressed this question, and one of the earliest was Aristotle, about uh, 2,500 years ago. And Aristotle just looked at objects around the earth, and for example, if I take an object, if I take a ball, and if I throw the ball around, what's going to end up happening is, well, the object is going to end up falling to the earth's surface and then eventually coming to rest. So Aristotle argued that at least for heavy objects, the natural state of motion, what the object would most want to do, is to be at rest on the Earth's surface. Okay, and I use the word heavy objects because Aristotle also tried to explain why you observe smoke particles rising, and he had to explain why those particles rise while other heavier objects fall to the earth and just come to rest. So at least for as far as heavy objects are concerned, he argued that the natural state of motion is to be at rest on the earth's surface. And so according to him, if you want to move an object, any kind of motion an object has is unnatural. Okay, you have to do something to it to keep it moving, and that something is what you can call a force, or you got to push it or pull it in order to keep it moving. And it made sense. If you think about it, if you observe phenomena on the Earth's surface, around you, you'll see that that's exactly what happens. Everything just eventually comes to rest, left to itself. But as it turns out, that this argument was not quite right, and people believed in this for almost 2,000 years. 2,000 years, they believed that this is probably what objects want to do. They want to be at rest on the Earth's surface. Then came Galileo around the 1600s, and Galileo argued that while being at rest on the Earth's surface is one of the natural states of motion of an object, it could also be moving at a constant velocity. So, according to Galileo, the natural state is either to be at rest or moving at a constant velocity. Again, when you say constant velocity, it means it's moving along a straight line at a constant speed. Okay. Now, Galileo's argument went this way. So, suppose you have, say, a block of wood on a floor, and you get it moving. Say, you kick it, and it starts sliding on the floor. Let's say it doesn't hit the walls, but eventually this block of wood is going to come to rest. And if I asked you, why does it come to rest, and you'll tell me, well, it's probably friction. It's friction that stops the object. So Galileo's argument was, well, the reason why the object comes to rest is because it was interacting with the floor. in which case you're not really studying the natural state of motion of the object. If you want to know its natural state, you have to isolate the object. You should make sure it does not interact with anything else. So Galileo came up with this, what we would call a thought experiment. He said, suppose you have a highly polished floor, okay, and on this floor, like the surface of of ice, or and if you had a highly polished floor and you had an object and you observed that this object was moving on this polished floor, he argued that if it was in an ideal situation where there was no friction, this object would keep moving. There's nothing that's going to slow it down. So based on those that argument, on that observation, or that deduction, he basically argued that the natural state of motion is either to be at rest or moving at a constant velocity. Okay. Then came Newton, and Newton kind of refined Galileo's ideas, and he refined it and stated all these observations in his three laws of motion. And that's what we're going to be focusing on now. Let's start off with Newton's first law. And Newton's first law states that if you consider an object that has no forces acting on it, there are no forces acting on the object, then what Newton argued, again, kind of picking up on Galileo's ideas, then if it is at rest, then it'll remain at rest. It won't do anything. If it is at rest, it'll stay at rest. But, however, if it is moving, then it'll continue to move in a straight line at a constant speed. Of course, straight line at a constant speed is what we call constant velocity motion. So in a sense, this entire phrase out here just means it'll continue moving at a constant velocity. So according to Newton, if there are no forces acting on an object, then the object will either be, if it is at rest, it'll remain at rest. And if it's moving at some constant velocity, it'll keep moving at a constant velocity. You don't have to do anything to it to keep it moving at a constant, for it to keep moving at a constant velocity. So in a sense, what Newton's first law is doing here is it's introducing this idea of a force. Okay, so it introduces this notion of force, and also in some sense, he introduces this notion of a net force, and we'll get to that in a little while out here. So what exactly is a force? Well, before we get to let's talk about what do we mean by a force? Well, for one thing, the force is a vector quantity. Okay, it's a quantity which has both a magnitude and a direction. Kind of makes sense because if you are pushing on an object, the way the object will behave will depend on the direction of the force, the direction in which this force is acting. Okay, before we get any more into the details, just introduce the symbols that we're going to be using for forces. So you'll see several of them coming up soon. Well, obviously the more obvious one, the little f, is reserved for special types of forces. This uppercase F is just for a generic force. Then you have special forces, special types of forces, and we have special symbols for them. And soon you will see symbols like N and W. And notice these are vector quantities, so I've got arrows on top of them. So those are the symbols that we're going to be using to represent forces. And the SI unit of force is, as it turns out, a Newton. And at this point, I'm not defining what a Newton is, but we'll get to this later on. So let me just say more on this later. And finally, we'll be using the phrase net force. And by net force, what we mean, well, first the symbol for net force, where the two possible symbols you sometimes will see written as with a sigma. Sigma just means the sum. It's just the way you read this is the sum of all the forces. Of course, force being a vector, it's actually the vector sum of all the forces. Or sometimes you might just see the symbol, the net force, written as F net. So remember, the net force is the sum of all the forces that are acting on the system, so on the object. So this, you want to read this as the vector sum of all forces acting on an object. Okay. Now coming back to Newton's first law, which says that an object either stays at rest or moves at a constant velocity. Okay, and if there are no forces acting on it, well, another way to say the same at Newton's first law is to say that if an object is accelerating, that means the acceleration of the object is not zero, then a net force must be acting on the object. In other words, again, the way you're thinking about it is the net force is the vector sum of all the forces acting on the object. So you go ahead, so if you see that an object is accelerating, what you do is you go ahead and figure out all the forces that are actually acting on the object. Then you take the sum of all these forces. Again, when I use the word sum, I mean the vector sum of all the forces. And then the answer is you're going to get the net force coming out to be non-zero. So, which means the net force acting on the object is is not equal to zero. Conversely, you can say conversely, if the net force acting on an object is zero, then the object cannot be accelerated. Okay, so it cannot be. So if you figure out, so it doesn't mean that no forces are acting on the object. You could have a bunch of forces acting on it, but you figure out the sum of all those forces, the vector sum of all those forces. We know how to do this because we know how to add vectors using the components. So you figure out the sum of all the forces acting on that object, and if suppose you find it zero, then that object cannot be accelerating. Well, what does it mean it cannot be accelerating? Well, if it is not accelerating, or if the acceleration is zero, it means the object is either at rest. So it doesn't mean that the object is not moving. It could still be moving because it could be either at rest or moving at a constant velocity. Okay, so let's make that very clear here. So if you say that an object is not accelerating, if the acceleration of an object is zero, it doesn't mean that the object is at rest. Well, that is one possibility. The other possibility is it's moving at a constant velocity, because remember, there is an acceleration if the velocity is changing. So if the acceleration is zero, the velocity is not changing, which means it could still be moving, but it's moving at a constant speed in the same direction. Well, Galileo also introduced the concept of inertia. Now, what is inertia? Well, inertia is the ability of an object to resist change in its state of motion. Okay, so for example, if you have a ball and a truck, both traveling at the same speed, you know that you could stop the ball, or you can change the state, or another way to say that is you can change the state of motion of the ball. You can bring it to rest, but it's next to impossible to stop the truck. And the reason is, we say, because the truck has a greater inertia, and because it has a greater inertia, its ability to resist any change in its state of motion is also greater. That's the qualitative or intuitive way of understanding inertia. How much resistance does it offer? How much resistance does an object offer to its change of to any change in its state of motion? Okay. Question then becomes, how does one measure inertia mathematically, or how does one go about measuring inertia? Well, inertia is measured in terms of the mass of the object. So that's a new physical quantity that we're introducing, the mass of the object, which is a measure of how much resistance does the object offer to any change in its state of motion. Well, the symbol for mass, the mathematical quantity, we typically use lowercase m or uppercase m, and the preferred unit of mass is the kilogram. Now, I just want to make put down an important make an important remark on the mass. Mass is not the same as the weight of the object. In common usage, everyday usage, we use the term mass is not the same as the weight. In everyday usage, we use mass and weight interchangeably, but in physics, these are distinct and different concepts. Okay, mass is a measure of the inertia, of the object, while weight in physics is a force. Okay, so completely different concepts. They are related, and we'll get to that later. But for now, just remember, you don't want to mix these two concepts, mass and weight. Keep them distinct. Okay, before we move on, just let's look at a few questions here and let you read through this one. Okay, so you've got two forces, let's say, acting on an object. One is a force which is acting to the east. So think about it. You've got an object being pulled by ropes, and one of the ropes is directed to the east, and the force that you're exerting on that rope is a 1 Newton force, and the other force acts to the north, same magnitude. So if I'm careful enough, I'll draw this arrow the same length as this one. So that's let's call that force F1, which is a 1 Newton force. This is F2, which is also a 1 Newton force. What can we say about the vector sum of these two forces? Well, based on the choices there, we have one thing that we know is one can go ahead and figure out the net force. And we know that the net force is going to be directed using the tip-to-tail arrangement or the parallelogram method, doesn't matter. You're going to see that the net force is going to be directed that way. That's the net force. In terms of the angle that it makes, well, since these have equal magnitudes, this angle right here is going to be a 45-degree angle. And as in terms of the magnitude, we know that the magnitude of the net force, since F1 and F2 are perpendicular to each other, it's going to be F1 squared plus F2 squared, and that's going to be square root of 2 newtons. And like I said, the angle is going to be a 45-degree angle. So the choice here is the vector sum points northeast, 45 degrees both north and east. So that's going to be your answer to that question. Here's another question. You've got an object and you're told that three forces are acting on the object. Two of them are shown to you. They have equal magnitudes, but they are in the directions shown. Question is, what is the direction of the third force? In fact, magnitude and direction of the third force if the net force is to the left. Okay, so we want to be able to sketch F3 so that when we add the three forces, we get a net force pointing to the left. Well, the way you approach this one is by first looking at the components of F3. Okay, why the F, since the net force has to be to the left, well, F3 should have, here I'm drawing the components of F3, a vertical component which exactly cancels F1. So I'm going to draw that arrow here, and the way I show that two arrows are the same length is by putting these marks out here, and that tells you that they have the same magnitude, even though they may not look that way. Now, the F3 has to have a horizontal component, and the horizontal component of F3 cannot be the same length as F2, because if that were the case, then the net force would just be zero. So what you want to do is you want to draw the horizontal component of F3 to be greater than that of F2. So the horizontal component, if I were to draw it that way, now we can draw the force F3. If these are the horizontal and vertical components of F3, then F3 is going to be a force which kind of points something like this: longer horizontal component and a shorter vertical component. And the answer that best agrees with our sketch is, in fact, C. Okay, so FC is going to be, F3 is going to be that force. Here's another question. An object is moving at a constant velocity. All but one of the following statements could be true. Which one could not be true? So, which of these statements could absolutely not be describing an object moving at a constant velocity? Okay. Let's go each statement. Let's go through these statements one at a time. The first one says three forces act simultaneously on the object. Well, you can have three forces acting on an object such that if you look at the vector sum of the three forces, you get zero. Okay, just going back to this example, suppose I had drawn this picture with the horizontal component of F3 exactly the same length as F2, then you would agree that the sum of F1, F2, and the F3 that I drew with the same horizontal component as F2 would result in the net force being zero. So yeah, you can add three vectors and get the zero vector. No forces act on the object. Well, if there's no force, then yeah, the object will be moving at a constant velocity. Let's go to D. Two forces act simultaneously on the object. Well, I can add up the two forces and get the zero vector, a zero force. But now look at C. C says a single force acts on the object. Well, if a single force acts on an object, then the net force can never be zero. Okay, so this is the statement which could not give you a situation where the object is moving at a constant velocity. So if a single force acts on an object, that object will always be accelerating. Okay, we've stated the first law. Now we move on, and now we're going to get into the more mathematical details of Newton's laws, and that's the second law. And in fact, the second law, Newton's second law of motion, is a mathematical equation that relates three quantities: the net force acting on an object, okay, so which is the vector sum of all the forces acting on the object, the acceleration of the object, and finally the mass of the object. So sigma f is the net force acting on the object, that's the acceleration. So it's a mathematical equation that relates these three quantities. Stated simply, Newton's second law says that the acceleration the acceleration is equal to the net force over the mass. Or another way to say that is net force is equal to mass times acceleration. And remember, when you're talking about the net force is the sum of all these forces that are actually acting on the object. Okay, so this is, by this equation I mean this is the vector sum of all the forces acting on an object. Okay, that is Newton's second law, which relates the net force, the mass acting on an object, its mass, and its acceleration. A few remarks on Newton's second law. When the direction of the net force is the same as direction of the acceleration. So if you add up all the forces acting on the object and the direction of that force that you get, the net force that you get is going to be the same as the direction of the acceleration. The second is now this equation also tells us what exactly do we mean by a force of 1 Newton. So the SI unit, let's focus on the SI unit of force, which is a Newton, obviously named after Newton. So from Newton's second law, which we just wrote down, from Newton's second law, we know that the net force is mass times acceleration. So this allows you to write the unit of force in terms of the basic or fundamental units. So 1 Newton. So what the second law says is 1 Newton is equal to 1 kilogram times 1 meter per second squared. Kilogram being the unit of mass. Acceleration is measured in meters per second square, which is 1 kilogram meter per second square. So essentially what we're saying here is Newton is short for kilogram meter per second square. Okay, so it allows us, so it's just a short way of writing of saying kilogram meter per second square. We just say a Newton. Well, there's another way to think about it. What this tells us is if you have an object of mass 1 kilogram, say you got a block of mass 1 kilogram, and you want to give it an acceleration of 1 meter per second, so that you want it to speed up by 1 meter per second every second, then you have to push it or pull it, and the amount of force that you're going to be applying is what we're calling 1 Newton. Okay, that's another way to think about it. Newton tells you how much, it gives you a rough idea of how much force you need to apply, or it allows you to calibrate the forces. So again, a direct application of Newton's second law, just a conceptual question, which is net force is mass times the acceleration. A constant force causes an object to accelerate at 4 meters per second square. The question is, what is the acceleration of an object with twice the mass that experiences the same force? Okay. Well, you can say the if thinking in terms of the magnitude, or we can, well, let's write it. The acceleration, one can write it as the net force over the mass. So what is the acceleration object with twice the mass that experiences the same force, which means you're exerting the same force on another object which is twice the mass. Well, from this equation you can see that if m is doubled, then obviously the acceleration is half the original acceleration. In other words, this object with double the mass is going to have half the acceleration if the same force is exerted on it. So if it is half the original acceleration, it means the acceleration is going to be 2 meters per second squared. Okay, let's end by stating Newton's third law. We'll come back to the third law later on. In a sense, Newton's third law is, I would say, a deceptively simple law of motion. Let's see what it says. What it says is, so let's look at the sketch on the left. What you're doing here is you are using a hammer. You're striking a nail with a hammer. You're exerting a force on the nail with a hammer, and so obviously every time you strike the nail, the hammer exerts a force on the nail which is pointing to the right. So if one object, in this case the hammer, exerts a force on a second object, which is the nail, then what Newton's third law says is that the nail is also exerting a force on the hammer, and that force is equal in magnitude. So here are the two arrows. This is the force that the hammer exerts on the nail, and the nail exerts a force of equal magnitude but in the opposite direction on the hammer. That's what Newton's third law says. Another way to state it is that forces always come in pairs. It's always an interaction between two objects. If one object exerts a force on another object, then the other object exerts an equal and opposite force on the first object. And these pairs of forces are called action-reaction pairs. Well, the third law gives us allows us to explain, say, how do you launch a rocket. So here you have a rocket filled with fuel. You power up the engines, you burn the fuel, and you have the burnt fuel is ejected from the rocket in the form of just gases. So you've got the main body of the rocket exerting a force on the ejected fuel. Okay, that's one force. The rocket exerts a force on the ejected gas. Now, what the third law says is that the ejected gases exert an equal and opposite force on the rocket in the upward direction, and that results in the rocket lifting off. Okay, so you can explain the launch of a rocket the launch of a rocket is a direct application of Newton's third law. Okay, it's two objects. In this case, it's the rocket and the ejected gas. Rocket exerts a force on the gases, and the gases exert an equal and opposite force on the rocket.